Mathematicians, it's our last set, 6-6 optimization. Optimization is not just being an optimist, but it's finding the best or worst in whatever mathematical case. It's finding a maximum or minimum. And we often call that an optimum because sometimes you want to have the least amount or the most amount depending on what your situation is. You can either find this with tech, finding a maximum or minima. You know how to do that if you threw a function into your graph. You could use the second calc and use the max or minimum in this case and find that way. Sometimes we don't have access to our calculators and we can use other methods, one of which is the x is negative b over 2a. It comes from the quadratic equation x equals negative b plus or minus square root of b squared minus 4ac. It's the front half of that, and that'll give you the x value for the maximum or minima. It works if you have a parabola. You don't always have a parabola, but that's when we turn to calculus to look at those turning points. The turning point can be a maximum or it can be a minimum. And we can tell that that happens when the slope is 0. It's a maximum if you remember, because you can tell it's a maximum if the second derivative is negative, meaning that the slope is decreasing. It has to be coming over the top. Or it's a minimum if the slope is increasing, pulling up around the bottom. So you can look at either a line graph of that, or looking at the second derivative. All right, just to be upfront, often the maximum or minimum aren't when the derivative is 0. If you're looking at a physical situation, you have limits on one side or the other, and often the turning points will have a derivative of 0, but this won't be the maximum because your endpoint really is the maximum. It's because mathematicians are jerks. Just be careful with that. So test, when you find these spots, test the maxima, the minima, and test the endpoints. All right, so let's try a problem. Here's some problem-solving methods that the text recommends. Draw a diagram. Yeah, diagram. Draw a picture. It takes you 2 seconds. It helps you visualize. Figure out what variable you're going to use and make a formula. So that's the next part. Diagram it, make an equation, find an equation, look at the first derivative, and then figure out with the second derivative or sign diagram, is it a maximum or a minimum, right? Pick that x value and use and solve the problem from there. Fine. Okay, so we're looking at a rectangular cake dish, cutting out squares out of a corner. So often they'll take a square piece of sheet metal and they'll cut out the corners, and they'll fold up the edges. Right, the machine can fold up the edges, and it can make a three-dimensional thing. Right, if you did that systematically, and you cut out a really small edge like that, right, a really small corner, it would make a wide but very shallow cake pan like that, right? If you had a little bit more of a corner cut out in the second one, right, it makes a little bit of a taller cake pan, but less wide. Yeah, you can kind of see the difference between those. Yeah, maybe you can't. Maybe we need to go for a road trip. Road trip. We're going to Ms. Koch's classroom because I know this is in there. There, that's what I'm talking about. Okay, so these are Ms. Koch's classes work, and these are all made out of a sheet of paper, right? And they cut the edges out, and you can see that this edge has been cut out a little less, and these edges have been cut out a little more. So this is a lot wider, but this has more volume, right? So you can see their shapes differ going from one to the next. And the ones in the middle have the greatest volume. The ones on the edge, these are really tall and thin, but you can't get much popcorn in there. And these, you can get a lot of popcorn in that one, right? and this one is like mostly like a tray, right? So you could maybe stack it, but if you're filling it with water, it has the lowest volume. So there's that maximum part at the top, and that's what we're trying to maximize. Yeah, so we're gonna look at that same sort of graph. All right, time to go back, sorry. All right, so if you cut out small corners, you'll get a small volume. If you cut out huge corners, you'll get a small volume, but right in the middle there's a sweet spot, and that's what we want to find. So they said, what size squares do you have to cut out to get a maximum volume? We're going to first make this x be the side length that we cut out. So this would be x, and also this would be x. Cool? They said it's a 25 by 40 centimeters. And so the volume is length times width times height of this cake pan. And the length is going to be this piece, right? This length, which is 40 minus 2 of these x's. And this length, the width, is going to be 25 minus 2 of these x's. That's what this piece is. Right? That's what this piece is. And the height, this part, is going to be just the x's, right? When you fold them up. I think I threw those. But when you cut that, when you fold those up, that's the height x. All right, so that length, width, and height should look like that. Length, width, height. And when you distribute these in and put them all together, blah, it looks like that. Fine, right? Maybe we want to put some limitations on what x can be. So we know x shouldn't be 0, or it doesn't have any height. X can't be bigger than half of this length, right? Because if you take, if this is 25 and you cut, the most you can cut this way is 12.5, and the most you can cut this is 12.5 before you get 0 volume, right? So that's what the limit there is about. Okay, fine. So we've got an equation for the volume. It's right here. All right, fine, moving on. If we take the derivative of that equation, right, that's the derivative of this, we multiply the 3 into the 4, you get the 12, drop that by 1, and multiply this in, so this should be 12x squared from this, and, minus 260 from this, right? And then this is, just plus 1,000. All right, so that's where they get this piece. Great. That's our change in volume based on how we change x. If you factor that and factored it some more, the math gods have been kind to us, and it turns into this. So we know that the derivative is going to be 0. This was going to be 0 either when this is 0 or that's a 0, right? So either when, if you set this equal to 0, you get x is 50 thirds, which is like 16 and a little bit. And if this is 0 when x is 5, so that's what where these come from. This one makes sense. I can cut out a 5 centimeter chunk, but since this length is only 25, the maximum I can cut out for one corner was 12.5. That's why we disregard this one. Go away, right? So this is our optimized x cutout. Okay, I don't know if it's a maximum or minimum. Logically, it should be a maximum, but you could find if it's a maximum or minimum with a sign diagram test. We can take this 5 and check the value of the derivative on either side. And so if you took a value that's between 0 and 5, like, I don't know, 1, and plugged it in here, you get 3 times 1, you get a negative answer here. You plug 1 in here, you get a negative answer there. You get positive times negative gives you this positive on this side. You'd figure out that it's negative if you picked a number like 6. And so you know if it's going uphill on one side, the slope's going uphill, and downhill on the other side, that must be a maximum. So that sign diagram tells you that 5 is the max. Alternately, you could throw it into a second derivative. You'd be taking the derivative of this, and so that's the 2 and the 12 give you the 24, and then there's your 260. So this is the second derivative, and you ask it what's the second derivative at x equals 5. So you'd plug 5 into here, and you'd get negative 140, which means the second derivative is negative, which means that the slope is going downhill. It's becoming more and more negative, right? Which means it's coming over the top. It's got to be a maximum. So either way, we've verified that the 5 is a maximum, and we can say that our maximum cutout value should be 5 for that spot. Great, done. Okay, and that's basically what you're doing with all optimization. You're building it in your head. What do we need to do? Build a formula that describes how things are changing. Find the derivative, maybe find the second, and use them to decide, is it a maximum, is it a minimum, and check the endpoints, because mathematicians are jerks. Cool?